Hello all, and welcome to your last week of semester one. Very exciting. This is your last week to get anything turned in. I'm giving you an extra day, so instead of having a quiz on Thursday, because we have a short week this week, we have a super short week next week, we're just going to do one quiz at the end of next week on those three things that you'll do today, tomorrow, and then on Thursday the 21st, which gives you an extra day to get in any missing or incomplete assignments for semester one. Once it passes Thursday at midnight, I'm going to start grading, and whenever I finish what's there, the grades will be posted on Infinite Campus, and that'll be final. So please, if you have questions about anything that's missing or incomplete, or you just want to know what you can do to raise your grade in the class, please let me know as soon as possible. So we're going to talk about the mean value theorem for derivatives. There's a different mean value theorem out there as well, but we're going to focus on the one for derivatives today. So get yourself ready for notes, and we're going to get started. So the mean value theorem for derivatives, we're looking at a couple problems from 4.2, and this theorem is an important idea, and the idea here is that if a function f of x is continuous on a to b, so we're looking at an interval of a graph, in this case, in this picture, it would be from here to here, and is differentiable on the interval a to b without worrying about the endpoints, what that's going to tell us is that there exists some point, oops, sorry about that, there is some point in between, which in this case is c. So what we'll say is that there is a c that is in the interval from a to b. So that's how we'd write it. So there's a c in between a and b, where f prime of c is equal to f of b minus f of a over b minus a. So what this says is that the derivative, or the tangent line slope, is equal to the secant line slope. So the idea here is that if we look at the picture, is that here's the secant, the average rate of change between the 2 points, and there's a point whose derivative is parallel. Now this can be helpful. And so one of the big tasks that we use the mean value theorem for is finding that place where the parallel line happens. So the first thing that we want to do is we want to, looking at our formula here, we want to find f prime, f of b, f of a and b. This is the idea here. So find the value, or values, it could be more than one, of c that satisfy the mean value theorem for f of x is equal to 3x squared plus 5x minus 2 on the interval from -1 to 1. So that means that this is our a value and this is our b value, right? We're talking about the interval there. So the first thing that we want to do is we've got this formula here, and it's going to be helpful to find f prime of x. We also want to find a and b of the original function, f of a. So f of x, we have a polynomial here, so we can use the product, the power rule. So 6x to the first, or 6x plus 5. F of b, well, b is 1, so this would be 3 times 1 squared plus 5 times 1 minus 2. So f of b would then equal 6. So 3 plus 5 minus 2. Here we have 3 times -1 squared, which is just 3, plus 5 times -1 minus 2, which is -4. Now, once we know these values, we can take it and plug it into our mean value theorem. So we have our tangent line, f prime of c, is equal to our secant line. So f prime of c we don't know, but we do know f prime, which is 6c plus 5. F of b is 6 minus f of a, which is negative 4, all over b, which is 1, minus negative 1. And this becomes the equation we're solving. So it's a complicated idea, but the nice thing is the formulas are very rarely going to be extremely complicated to solve. So we've got here 6c plus 5 is equal to 6 plus 4, which is 10, over 1 plus 1, which is 2. So 6c plus 5 is equal to 5. 6c is equal to 0, so therefore c is equal to 0. And since we're just asked to find the c value, it is, in this case, directly in the middle of our interval from a to b. Let me know if you have any questions about the mean value theorem for derivatives, or if there's anything else I can help you at the end of the semester. Talk to you later.